This is a list of keywords that you should already know. If you are unsure about any of these words, you need to go back to your notes and make sure you can give a clear definition of each of these. Remember, for the extended questions, you need to be able to give technical answers. And without a technical answer for each of these keywords, you will lose marks in the exam. Task number 1, go back through these keywords and make sure that you can explain what each of them means. Last lesson we looked at the factors affecting the performance of a processor. Remember, there are 3 C's: clock, cause and cache. There are other things that can affect the speed of a processor. However, it's important that we think about these inside the processor to get the best performance that we can have. Remember that speed is measured in hertz, sometimes gigahertz. Generally speaking, the more cores, the faster the processor. The more cycles, the faster the clock speed. But remember that this can have a disadvantage. If we overclock, it can cause overheating and parts of the motherboard to burn out. Remember, the third C is cache. This is expensive memory, but it's fast and inside the CPU for common instructions. In this topic, we're going to look at pipelining and how this affects the speed of a processor. This actually does link to some of the other specification, particularly in the A-level specification in second year, and it also looks at 1.2 and has links to other parts of the specification, and I've signposted these throughout the lesson. During the fetch, decode and execute cycle, parts of the processor would be idle, and in traditional computers this is what happened. First of all, you'd fetch an instruction, then you'd decode it, then you would execute it. Well, that is not an efficient way of doing it, and we can speed up a processor by pipelining. Think of this like in a factory. We have a product which will go through different stages of its production before it's packaged and sent out to market or to the shops. If we had to wait for every single product to be finished before we could start the next one, this would be really inefficient. So what we do is, if we finish one part of the product cycle, we move on to the next, and the next product can start to be made. So pipelining makes the CPU more efficient, because as one instruction is fetched, the next instruction will be decoded and there'll be another instruction being executed. We are going to create a production line for a paper aeroplane. Each of you will have a different step. Once you finish your step, you'll pass the paper aeroplane to the next person in the production line. Let's time and see how long it takes to make 3 paper aeroplanes. That was the inefficient way. In a production line, remember that once we have finished our step, we're going to repeat the same step whilst the next paper aeroplane has been started to be made. This is the pipelining process. Here is an abstracted view of pipelining. You can see we've got different pipelines. In pipeline 1, it fetches, decodes and executes an instruction. But pipeline 2 has already fetched its first instruction, so it is decoding its second instruction and then executing that instruction. It will then fetch the next instruction. When we are pipelining in a CPU, it can be divided into an instruction pipeline and an arithmetic pipeline. These two parts have very different roles. The instruction pipeline consists of the different stages which the instruction is moved through the processor. So it's fetched, it's decoded, buffered, and then executed. Whereas the arithmetic pipeline is the actual part of the operation. So we can break that down, and these can be overlapped as they are performed. So if we're adding 2 numbers together, we're going to need both of those values, so they might overlap in their running. If you're confused about this, don't worry too much about it. You need to go and watch the Craig and Dave video to give you a little bit more information on pipelining. So pipelining is really common in modern day processors now, and you see this happening in personal computers and all CPUs. Although in theory all pipelines work the same, There are slightly different types of pipelines that can be used in the CPU. For example, a graphics pipeline. Think of this when you load an image on the internet. If you load a certain type of image, you might see it looks blurry to start with. That's because it started to load part of the picture but hasn't loaded all of the pixels, and it chooses to start to load the first part of the image and will leave sections so it will gain in clarity as you gain more data. This is pipelining in action. Here is a simple piece of code. It's an algorithm for a game for kids to determine which house they are going to be in at Hogwarts from Harry Potter. You can see it's got simple selection. You might want to download this PowerPoint and run it through so that you can see some of the animations that occur over the next couple of slides. This is a non-pipelining CPU. The first instruction it will fetch will be on line 1. The first clock cycle, it will fetch this instruction. In the second clock cycle, it will decode it, then it will execute it, then it will fetch the next one, decode that one, and execute that one. This is massively inefficient. Look at all the idle space. And for us just to get to the third line of code, we're on the 6th clock cycle already. Again, to fully understand this, you probably need to download the PowerPoint. Now, this is pipelining in a program. You can see the clock cycles on the left hand side and the console in the bottom. So the console is what I would expect to be printed on the screen. It's the same program. You can see the fetch instructions in green, the decode in red, and the execute in yellow. In the first clock cycle, you would expect for the processor to fetch the first instruction. So it is fetching the first instruction. In the second clock cycle, it's actually starting to decode that same instruction. But the fetch would otherwise be idle. So it's deciding to fetch the second instruction. And when we move down to the second, third and fourth, you can see the progress of the different lines of code through the fetch, decode and execute cycle. So in theory, at every clock cycle, you're going to be fetching one instruction, decoding another and executing another. When we're using selection, however, and we meet a selection statement such as an if, else, if, elif and else statement, then we call this branching. This is the computer telling the program that it needs to go to a different part of the program to execute that code and follow the flow of control through the program. This only happens in high-level programming languages. Now remember, high-level programming languages are Java and Python, where a lot of the commands are built into the program. Now when we're running a program through, obviously the user doesn't run at the same speed as the clock. Remember, there could be millions of instructions which are processed every second. So we can assume there's some idle time here. As the program runs through, it gets to line number 3 and it says, the user, please input the house that you are in. Obviously, while it's waiting for the user to input that value, there is some idle time, or you'd imagine there would be some idle time. However, the CPU doesn't actually wait for the user to input a value. It has something called a scheduler, and this is actually managed by the operating system. It's one of its functions. And a scheduler assigns a priority to each different task and will decide which task it's going to run. So rather than waiting, it will start on other processes. Another process will start, and when the user does put an input in, that will cause an interrupt. If you go to the specification points 1.2.1, we'll cover schedulers, the function of the operating system, interrupts, priorities in this section, which is called software and system development. So when we are using a CPU which has pipelining and we're fetching instructions, when we get to a branch, such as this branch, we're currently executing line number 4, so we're checking the user input to see if it's equal to Gryffindor. If it is equal to Gryffindor, it can continue to run the program. It is decoding line number 5 currently, so in the next clock cycle it will print "You are brave and reckless." However, it's just fetched Elif house equals Slytherin. There may be an instance when you are using pipelining in a CPU and you reach a branch that some of the instructions won't need to be run. In this instance, when we get to execute line number 4, if house equals Gryffindor, if they haven't typed house equals Gryffindor in, then we've actually already fetched line number 6 and we have decoded line number 5. Well, we don't need line number 5, so what we would actually do is do something called flushing the pipe, which is removing any instructions that we don't need. So they would just be removed and we'd continue running the program. So in summary, a pipeline frees up the CPU so it is more efficient. CPUs which don't support pipelining are likely to be slower and will have idle parts. Therefore, we can free up this idle space by using pipelining. This means that we are running fetch, decode and execute cycles in the same clock cycle. This is particularly good when you're using graphics or having to render graphics. Please stop the video now and answer the past paper questions. Make sure that you don't look at the answers first, try and write out your answers and then use the mark scheme to mark your work.